Good morning. My name is Matthias Fresacher, and today I'm going to tell you about joint work I did together with James East, Azeef Muhammed and Tim Stokes on finding a categorical representation of DRC semigroups. To begin with, a quick overview of what this talk is all about. And it's actually going to be two talks in one. First, I'm going to go through a speed talk, and then I'm going to go through a talk proper. In the speed talk, I'm just going to try and give you a big picture summary of what this project was all about. The key aim here is to try and give you an idea of what the destination is that I'm trying to get to. And this will hopefully make the talk proper as accessible and easy to follow as possible for you. Because of this though, I am going to keep definitions to a bare minimum in the speed talk. In the talk proper, I'm going to repeat everything again with all of the missing details, including the definitions we are going to need. I'm also going to outline the motivation for this particular project, which will nicely lead into the main theorem we were able to prove. I'm going to give an outline of that proof and go into some of the details, but I do want to spend some time looking at the particular history of this research program, as well as putting our result in its appropriate context. Towards the end, I'm going to go through some applications of this work, as well as some possible future directions for this research program. So let's get into it with the speed talk. And this is going to be a tale of two cities. On the one side, we have semigroup city. So that is a set together with a binary operation that is associative. On the other side, we have category city. So this is where we have a category, which I'm going to think of as a collection of objects denoted by points. We have a collection of morphisms denoted by arrows that map between our objects, where every object must have an identity morphism. And we need to have a way that composes morphisms that is associative. Over on our semigroup city side, well there the binary product is defined for every possible pair. This means we know the full Cayley multiplication table. So for example, if I'm looking at the zero twisted brow monoid of degree 2, this would be its Cayley multiplication table. However, on the category side, the binary operation is only defined for some pairs, specifically where the domain and range of our morphism matches appropriately. Because of this, we only know the partial Cayley multiplication table. So in this example, this is what our Cayley multiplication table would look like. We can see it's mostly empty because a lot of the compositions just don't exist. A, for example, can't be composed with A, we can't compose it with B, nor with the identity on A. All we can compose it with is the identity on B, in which case we would get back A. Why do we care about categories? Well, because they need less information. And this leads to the natural question, if I start off with a partial binary operation, can I recover the full binary operation? Spoilers, yes we can, thanks to the Ehresmann, Shine, Nemburipad, ESN theorem. But this is only true for inverse semigroups. Since then, there's been a lot of effort to try and generalize this to other semigroup families. And today, I'm going to talk to you about the latest installment in this particular research program for DRC semigroups. But this need for less information here is somewhat misleading because sadly, nothing in this world is for free. The word category does a lot of heavy lifting on the previous slide. Generally speaking, our categories need additional structure, and this is where in essence the missing information is hiding. In general terms, the bigger our semigroup family, that is if we weaken our axioms from say inverse semigroups to DRC semigroups, the more structure we need on the category side, for example moving from an inductive groupoid to a chain projection category. So the classical ESN theorem says that there's an isomorphism in the category sense between the category of inverse semigroups and inductive groupoids. And today I'm going to work up to the newest installment in the ESN theorems. That is our result for the category of DRC ESN theorems, semigroups rather, being isomorphic to the category of chain projection categories. So let's get into the talk proper, and let's start off in semigroup city with the definitions for the semigroups we are going to need. Obviously, the main object for this study is a DRC semigroup. So that is a semigroup together with two unary operations D and R. By unary, I simply mean a map from S to itself. These are called the domain and range operations. I am actually going to start off though with just defining a D semigroup, so we don't have the R operation. For a D semigroup, for every A and B in my semigroup, these three axioms need to hold. A common theme in this talk is going to be a lot of duality, so I can also talk about an R semigroup. So here we don't have the D operation, but we have the R operation, and we have the dual version of each of our three axioms. I can upgrade this slightly into a RC semigroup, where C stands for congruence, and here I need to add the congruence axiom. But it actually turns out that these three axioms imply this last one, so this one now is redundant, so we're going to get rid of it. If I take a dual again, I end up with a DC semigroup satisfying these three axioms, and that now nicely leads us into the DRC semigroup, where we have our DC axioms, we have our RC axioms, and we have two more axioms that link the domain and range map. So a DRC semigroup, all of these 8 axioms hold. The DRC semigroups contain quite a large range of common semigroup families, and let's have a look at those now. So the DRC semigroups contain the star regular semigroups. These in turn contain the regular star semigroups, and I apologize for the naming, that is historical, not my choice. And the regular stars, they contain the inverse semigroups. DRC semigroups also contain the Ehresmann semigroups. Ehresmann contains the restriction semigroups, and these in turn get us back to the inverse semigroups. Sitting inside the center here, we also have our DRC restriction semigroups. I'm actually, though, going to start off with a not DRC semigroup, but a regular semigroup that sits off just to the side here. So in a regular semigroup, we have the regularity axiom holding, which basically says for every element in my semigroup A, there exists some other element B such that AB is equal to A. This actually leads and implies the existence of a semigroup inverse. So typically this is denoted A primed, and a semigroup inverse, well, it satisfies this regularity condition, but the inverse is also its own, if we take the inverse of the inverse, that is now the inverse of the thing that we started with. So we have sort of the axiom in the other direction. So for us to have a semigroup inverse, these two conditions need to hold. It's really important to stress, though, that in a regular semigroup, this semigroup inverse need not be unique. There could be lots of different elements that satisfy this particular property. If I now move all the way down into our inverse semigroups, well, here we do have a unary operation denoted by the inverse. And we have this because the axioms of the inverse semigroup say that the semigroup inverses are now unique. There exists just a single unique one, and that's precisely what this map is doing. So we can map an element A to its unique inverse A raised to the power of -1. And because it is a semigroup inverse, obviously this particular property needs to hold. Now, a good example of an inverse semigroup, even though somewhat trivial and a little boring, would be groups where the semigroup notion of the inverse is actually the same as the group notion of an inverse. Now, a semigroup inverse is a DRC semigroup, but DRC semigroups have these D and R maps. So where do they come from? Well, I can define my domain map making use of the inverse. And dually, I can define the range map if I swap the product here. If I now move up into the regular star case, well, here I don't have an inverse operation, I just have a star operation. This still satisfies the regularity condition because, well, they are a subset of our regular semigroups. But the star is also an anti-involution. And by that I mean if you apply the star twice, you get back where you started. And if I apply the star to a product, I swap the order and then just apply the star to individual elements. In fact, these three properties actually imply that the star is the semigroup inverse, or at least a semigroup inverse. There could be multiple. A good example of a regular star semigroup are the diagram monoids. So this is an animation of the multiplication operation of the diagram monoids, so that is concatenation. And the star operation, well, that takes a diagram and it just flips the top and the bottom rows in the obvious way. The domain and range map, well, we can define those analogously like we did in the inverse case, but now we're just using the star operator. If we now move up a little bit more into the star regular case, well, here we still have our star operator, but our axioms look a little bit different. Here we encounter the Green's H relation, which I don't want to spend much time on, but just to roughly say that in semigroup theory, if two elements are H related, they're about as close as you can be to being equal without necessarily being equal. They are equivalence relations, so the H relation is an equivalence relation, so we can look at the equivalence classes. In particular, I want to look at the equivalence class of A star. Sitting inside of that, there's going to be a unique element, I'm going to call it a dagger, that satisfies our regularity condition. This is actually called the Moore-Penrose inverse, this A dagger. Good example of star regular semigroups include the Z twisted diagram monoids, as well as your multiplicative monoids, so they're just n by n matrices. So for example, we can look at 2 by 2 matrices over the complex numbers. Multiplication is just the standard matrix multiplication. What is the star operator? Well, that is the conjugate transpose. And our dagger operator, well, that is a little bit harder to explicitly state. So I've just calculated it for this particular example matrix. And it just so happens to be that it's a multiple of the star. But in general, it could be a lot more complicated than that. And then if we actually see whatever I've written out here, it's precisely this identity for that particular matrix. How do we define the domain and range map? Well, again, we're just going to make use of the dagger, the Moore-Penrose inverse, to do that. If we now swing over onto the other side here, onto the Ehresmann side, well, an Ehresmann semigroup already comes equipped with a domain and range map. So because it is a subset of the DRC semigroups, obviously the 8 DRC axioms already are going to hold, but we have some additional structure. So we have that the image of the domain map, everything commutes in that image, and we have the same true for the image in the range map. In fact, it actually turns out that one implies the other in the presence of these other axioms, so there is some redundancy here, but I just wanted to explicitly state both of these properties. Good example of an Ehresmann semigroup is the monoid of binary relations. So for example, if I take a set X, say 1, 2, 3, I can have some binary relations, say 1, 2, and a different one, 1, 1, and 2, 3. How do we compose binary operations? Well, essentially it is like the transitive property. I need to take a step in my first relation and then a step in my second relation. So if I go from 1 to 2, well, I can't make use of the first relation, but I can make use of the second relation to go to 3, so we end up with a step from 1 to 3. It is a monoid, so we need an identity element, and that is just all of the reflexive pairs for each of the elements in our original set. What would be the domain of a relation? Well, basically, we just look at the first component in our pairs. That's the obvious domain, but it has to be a relation, but we can make use of our reflexive trick and sort of just write the same element twice. And similarly, what is the range operator for a relation? Well, now we're just going to look at the second component of a relation. So that is Ehresmann sorted. Now if we go down to the restriction semigroups, here again we have a domain and range map, and because they were a subset of the Ehresmann semigroups, we have our DRC axioms, we had our 2 Ehresmann axioms, and now we have, well, we're going to look at the right restriction semigroup first, so a one-sided version. Here we have the extra axiom that this holds as well, so there's a little bit more commutativity, or in essence commutativity, happening. Dually, we can look at a left restriction semigroup, and this is where the dual axiom holds. But what I'm actually talking about in this diagram here when I say restriction semigroup, I mean the two-sided restriction semigroup. So that means both the left and its dual that we just saw, the right version of that axiom, hold. Both of them are true in this restriction semigroup that I mean here. Then we also have the DRC restriction semigroups, which I'm not actually going to define today because they're a little bit more involved, but you can sort of get a sense of the properties they might have just from where they sit in this particular diagram. And just to recap, because this was quite a heavy slide, the main object of study for this project and all we basically need going forward is the DRC semigroup. Recall that has a domain and range map, and these 8 axioms hold. That's all we basically need to remember from this slide. So now let's go into the category definitions we are going to need. So for that, I'm going to take a category C, which recall that is a collection of objects, which I'm just going to denote as points. We have a collection of morphisms, which I denote as arrows between our objects, such that every object has an identity morphism. And we have a way to compose morphisms that is associative. We're going to need to understand the notion of a small category, which basically just means that our object and morphism collections are both sets. We then have a domain and range map which takes a morphism and maps it to an object. So if I take the morphism A here, this arrow, the domain map, well, that basically asks where is it mapping from? That would be the capital A here. And the range map, where is it mapping to? Well, that would be the capital B. And hence we can then see when does composition make sense, when can we compose two morphisms, precisely when the range of the first equals the domain of the second. We're going to play a slight notational trick. We're going to identify our objects with our morphism set. And the way we do that is if we take a object A, I'm going to identify that with the morphism that is the identity morphism on that object. So because of this, our domain and range map, at least we're going to think of it as mapping from morphisms to morphisms. The first category we're going to encounter is the groupoid. So here, all of the morphisms have inverses. As the name suggests, this generalizes the notion of a group. But because it is a category, we only have a partial binary operation. Composition only makes sense where the domain and range appropriately matches, compared to in the group case where obviously the binary product is defined for every possible pair. So we need to be now careful in the next step. At times, we're going to be looking at a specific instance of, say, a groupoid or some other category in sort of as an abstract algebraic object. In that case, there are always going to be a small category. However, I'm also going to be talking more generally about, say, the category of all groupoids. That obviously is a large category, the opposite of being small. So just be careful of that distinction if I'm talking about a specific instance or the category of all of them. Next, we need to understand an ordered category. And for this, I'm going to put a partial order on our morphisms, and these satisfy some axioms, which I'm going to go through pictorially. So suppose I have a morphism A, and suppose I have, we have its domain, and we have its range, and suppose I have a second morphism B, we also have its domain and its range. And let's suppose that A sits underneath B in our partial order. Then, according to the axiom, the domain of A also has to sit underneath the domain of B, as well as the same thing has to be true for their ranges. For axiom 2, well, let's consider a morphism that I can compose with a second morphism C. So we have AC. Suppose we have another morphism B that composes with D to give us a morphism BD. And the hypothesis says, well, let's suppose A sits underneath B and C sits underneath D. Then our axiom says that AC must also sit underneath BD. Now, for the final axiom, we're going to start off with the left ordered category, so the left version of this, so axiom 3 left version of it. Let's take a morphism A, look at its domain, and take any object sitting underneath it in the partial order. Then the axiom says there exists a unique morphism U that sits underneath A such that its domain is precisely that P. If you're familiar with it, this is typically called the left restriction of A to P, but I'm not going to use that terminology in this talk. There is also the right version of this, so this would give us a right ordered category. So we still have our morphism A, but now we look at its range and consider any Q that sits underneath the range. Then the axiom says there has to exist a unique morphism V such that V sits underneath A and the range of V is precisely Q. Again, if you're familiar with the terminology, this would be called the right restriction of A to Q, but I'm not going to use that terminology in this talk. So there are a few more categories we're going to need, and I'm just going to go through a roadmap to give you a sense of where we're trying to end up. So we just encountered the groupoid and the left and right ordered categories. I'm going to combine these two to give us an ordered groupoid. And then I'm going to take this one step further to give us an inductive groupoid. I'm also going to take these one-sided left and right ordered categories and create a two-sided biordered category. So these two categories are actually the main stars of this talk, and they're the ones that we're going to see quite a bit. So let's go into the details and have a look at the inductive groupoid. For this, let's start off with a groupoid. Recall that here all of the morphisms have inverses. And then I'm going to take a left-ordered category. So we have, well, because we're going to have two partial orders floating around, I'm going to use a subscript L to denote the left partial order. It satisfies the first two axioms, and because it's a left-ordered category, it satisfies the left version of axiom 3. If I take all of these properties and I add to it a fourth axiom, the fact that if two things are underneath each other, then so are their inverses, then I get my ordered groupoid. Now, if I actually take all of these properties, they then actually imply that the right version of my axiom 3 holds, even though we started off with a left-ordered category. Alternatively, I could have started off with a right-ordered category here. We can swap out all of these partial orders for their right ones, swap out our axiom 3 for the right version, then this implication here will give us the left version of axiom 3. If I take an ordered groupoid and I add to it the extra condition that our object set is a meet semilattice, so that is every two elements have a greatest common lower bound, then this is what we call an inductive groupoid. As we can see, the difference between an ordered groupoid and inductive groupoid is just the extra property on what is the object set. At the category level, these axioms are exactly the same. So for the next couple of slides, I'm going to use them a bit interchangeably because I'm just going to analyze the category structure. But obviously later on, we are going to need, at least in the background, the structure on our object set as well. And notationally, I'm going to refer to my categories as follows. So for example, the category of all inductive groupoids. What is our underlying category structure? It's an ordered groupoid. And what was our object set? It was a meet semilattice. So now let's look at this inductive groupoid in a little bit more detail. So for this, I'm just going to take a category C, and I'm going to turn this into a left-ordered category by putting a left partial order on it. From that, we saw how we can then construct an ordered or inductive groupoid with the left partial order. Alternatively, with the same category, I could have turned it into a right-ordered category by putting a right partial order on it. Again, I can construct the corresponding ordered or inductive groupoid from that with the right partial order. So then the question is, are these two categories actually the same? Well, yes, they are, because in fact, the two partial orders are the same. That axiom 4 is quite powerful in the ordered and inductive groupoids. So because of this, if I now just take an ordered or inductive groupoid, I'm not going to worry about subscripts on the partial order because they're actually the same anyway. So now we just want to have a quick look at the axiom 3. So we have the left version of it holding. Recall that this says that if I take a morphism A, I look at its domain, I take any object P sitting underneath it, then there has to exist a unique morphism V that sits underneath A whose domain is precisely P. We also at the same time have our axiom 3, the right version, holding. So recall for this, we now look at our range of A, take any object Q sitting underneath the range of A, then the axiom says there exists a unique V that sits underneath our A such that the range of V is precisely Q. But by axiom 1, the range of U has to sit underneath the range of A. So we can actually let Q be the range of U. So that would mean our Q actually sits up here. We still get that unique V. And in this case, it then actually holds that U is equal to V. These are the same. So if we update our drawing here, we just have the one morphism here. And logically, the domain of V then would also be equal to P. The reason I bring this up is because we're going to see a similar construction towards the end of the talk, but the outcome of this analysis is going to be different. So just keep that in mind. So that is our inductive groupoid sorted. Now let's have a look at the biordered category. So for this, I'm going to take a left-ordered category. It has its three axioms that hold. I'm also going to take a right-ordered category where its three axioms hold. And I just want to point out here that we have the same underlying category and we put two different partial orders, the left and the right, on it. If I take all of these properties and I add to it the extra condition that on the object set the two partial orders are actually the same, then I have my biordered category. So now I have two partial orders on my set, both the left one and the right one. Now that was a fair amount of different categories to go through with some very subtle differences between them. So let's just compare the different categories that we encountered. So that was the left and right ordered category, the biordered category, and our inductive or ordered groupoid. So we had our axioms 1 and 2, and they held in all four of our categories. We then had our axiom 3 left. So this obviously is true in the left-ordered category, but not in the right-ordered category. In the biordered category, the left partial order satisfies it, and it's also satisfied in our ordered or inductive groupoid. Well, duly, if we're now looking at the right version of axiom 3, that doesn't hold in the left-ordered category, but it does hold in the right-ordered category. And our biordered category, the right partial order satisfies it, and it is satisfied in our ordered or inductive groupoid. We then have our axiom 4. That is not satisfied by any of our ordered categories, but it is satisfied by our ordered or inductive groupoid. And then finally, where are the two partial orders the same? Well, we need two partial orders for that statement to even make sense. In the biordered category, well, we saw by axiom 5, that's the case, but only on the object set, whilst in our ordered or inductive groupoid, it's the case everywhere. So that brings us to the history. So going back in time, symmetry arises naturally in nature, and this led to the notion of an abstract group by Cayley in 1854. Symmetries also arise in differential equations, and this led to the notion of a pseudo-group by Lee in the 1880s. But there was no abstract structure for these until eventually two solutions were found in the 1950s. One was using inverse semigroups by Wagner and independently Preston, and a second one using groupoids by Ehresmann. Schein, then in 1965, links the work of Wagner and Ehresmann by providing a structure theorem for inverse semigroups making use of groupoids. Then Buripard in 1979 then generalized this result from inverse semigroups to regular semigroups. So that brings us to the classical ESN theorem as we know it today, as formulated by Lawson in 1998. And basically what this is telling us that if I take my category of inverse semigroups, that is isomorphic in the category sense to the inductive groupoid. As I mentioned on the last slide, Buripard then in 1979 proves the analogous result for the regular semigroups. But here we need to be a little bit careful. We don't have a category isomorphism, we just have an equivalence of category, so a little bit weaker, and it's to some category of groupoid. I'm not going to go into the details of that. Since then, there's been a lot of work to try and generalize this to other semigroup families. And first up was Lawson in 1991, where he proved the result for the Ehresmann semigroups. So that is the category of Ehresmann semigroups is isomorphic to the Ehresmann categories. So that is a biordered category where our object set is a meet semilattice. In the same paper, he also proved the analogous result for the restriction semigroups. Before I continue, we need to understand projection algebras. So for this, let's take a DRC semigroup S and consider the whole semigroup sitting in front of us. Sitting inside of that, we have our set of idempotents. So that is A is equal to A squared. Sitting inside of that, we have our set of projections. So not only are they idempotents, but the domain and range map is the identity map on our set of projections. An alternative but equivalent definition comes from the DRC axioms, where we can see that the image of the domain and range map actually is the same, and we can make use of this common image to define our set of projections. Unfortunately, our projection set is not always going to be a sub-semigroup. Because of this, we need to introduce a more abstract algebraic object called a projection algebra. So this is where we have a set, I'm going to call it P, and we have two families of unary operations. So one for every projection, so we have some feeders, and we have one delta for every projection. And these need to satisfy these 10 axioms that I'm not going to dwell on at all. If you're familiar with it, do be careful though. This is different to Peter Jones's original formulation of a projection algebra because he made use of two binary products, whilst here we have two families of unary operations. But the two are equivalent if we make use of these two identities. Now, we can start off with a DRC semigroup and turn it into a projection algebra that satisfies these axioms. And to do that, we take our set in the projection algebra to be precisely our set of projections, hence the terminology. And then how is feeder defined? Well, it's defined in terms of the range map, and dually delta is defined in terms of the domain map. And because of our DRC axioms, if we were to chase it through, you would then actually see that these axioms hold. Now, strictly speaking, we need to be a little bit careful here. I started off with a DRC semigroup. So strictly speaking, the projection algebra that I just went through with you is a DRC projection algebra. In a moment, I'm going to go through and look at the regular star semigroup. And they also have a projection algebra, strictly speaking, a regular star projection algebra. The difference here being that we would have strictly more axioms. They were a subset of our DRC projection algebra. So to sort of keep track that we have a stronger projection algebra, in that case, I'm just going to put a star here in reference to the regular star. And towards the end, we're also going to encounter the inverse semigroups. They also have a projection algebra, the inverse projection algebra, which is even stronger. So we have even more axioms here. But in fact, you've already come across the inverse projection algebra because this is precisely the meet semilattice. So just keep these connections of these three different types of projection algebras in mind for the end. So now let's go into and have a look at some of the more recent developments in this area. So in 2024, East and Muhammed proved the result for the regular star semigroups. That is, the category of regular star semigroups is isomorphic to the category of chain projection groupoids. Here, the category structure is an ordered groupoid, but our object set is now this stronger version of a projection algebra than I just went through with you, that special starred version. In the same year, D and Wang also proved the result for the DRC restriction semigroups. And at this point, I should mention there are other generalizations by many other authors that don't quite neatly fit into this picture. A lot of work has been done in this space. It is quite an active area of research. So that brings us to the DRC ESN theorem, and that's the key result I want to talk to you about today. So this is the statement of the theorem. And basically what it's telling us is that the category of DRC semigroups is isomorphic to the category of chain projection categories. In terms of a proof of this, well, we first need to find the right axiomization of the category. For us, that is a biordered category. And we need the right structure on our object set. For us, it is the projection algebra, the exact one that I just went through in a little bit detail previously. Well, that was a pretty quick two-line proof. It is actually a little bit more involved than that. So let's have a look at this isomorphism in a little bit more detail. So on the left-hand side, I have my DRC semigroup S, and I need to get to a chain projection category. And I'm writing it at the bottom here because we have a bit of constructing to do. So we already saw how we can go from our DRC semigroup to a projection algebra, the abstract notion of that. So I'm going to let my object set be the set of projections. That takes care of my projection algebra component. For my morphisms, well, I'm going to use the entire semigroup here. And at this point, it's useful to draw a picture. So if I have a semigroup element A, that's some morphism, that's some arrow. Likewise, a different semigroup element B would be a different arrow. Now recall that the image of the domain and range map is precisely the set of projections. So if I now ask, well, this morphism A, where does it map from? Well, if I take the domain of A, the image of that is a projection. That is a valid object. That is where it's going to map from. Where is it mapping to? Well, if I take the range of A, that is also a projection, hence an object. That is where it's going to map to. Hence, we can see that the names and the DRC axioms, in a moment at least, make some canonical sense. We also have B. Where does that map from? Well, from the domain of B to the range of B. And in this example, let's suppose these two are equal. We do need some identity morphisms, and for this recall that the domain and range map is the identity map on our set of projections. So if I look at this D of A, that is a object, that is a projection. Let's say it's projection P. But P is also a semigroup element, so it's a morphism, and I can ask where does it map from? Well, it maps from the domain of P, but that's just P. And where does it map to? Well, the range of P, but that is also P. So we precisely have that morphism from P to itself. And obviously the same is true for all of our other objects. We do need a way to compose our morphisms, and for this I'm just going to try and use the semigroup product. So I'm going to hope that the semigroup product AB maps from the domain of A to the range of B. But for this to work, we need the domain of AB to equal the domain of A. Is that actually true? Well, with perfect foresight, recall these two DRC axioms, and let's have a look at the domain of A and B. We can make use of our first axiom here. Here we find the domain of B, but we're assuming that is equal to the range of A. Let's make that substitution. Here we can make use of our second axiom, and we just get the domain of A. Yes, these two are equal as we had hoped. By a dual argument, the range of B is going to equal the range of AB. So yes, our composition using the semigroup product works. And because of this, we actually get associativity for free because, well, our semigroup product already is associative by definition, so now composition is also associative. So that gives us a category C. So that is the C here sorted. Next, we need to take care of the P, the projection category part, but for that we need to have a biordered category. So let's construct this biordered category. So recall what we had. We had our object set being the set of projections, and we had our morphism set being the entire semigroup S. We also had our unary operations D and R from S to S. Well, in the category side, I can use those same domain and range maps. I'm now going to put a partial order on the projections, well, only on the projections. And it's going to be defined as follows. So P is less than Q if P is equal to QPQ. For our biordered category, we need two different partial orders, the left and the right, and it needs to be for the entire semigroup. So I can define these now, and just be careful, these are not Green's pre-orders, even though notationally that's what it looks like here. I'm going to define these pictorially. So we have a morphism A and we have a morphism B, and suppose A sits underneath B in the left sense. Well, by definition, this means if I take the domain of B, there has to exist a P that sits underneath the domain of B in this order on our projections, such that A is equal to PB. Remember, we're in the semigroup here, so this product makes sense. This actually implies that P is equal to the domain of A, so this picture that I've drawn here actually is accurate. Well, we also need the other partial order, so let's take a C, and suppose this sits underneath B in the right sense. Well, by definition, this means if I look at the range of B, there has to exist a Q sitting underneath the range of B, again in this order on our projections, such that C is equal to BQ. Likewise, here Q then actually has to be the range of C. Now recall, we had the inductive groupoid case where we had a similar constructions, and we then wondered, well, what if the range of C also equaled the range of A? What if Q was up here? Recall in the inductive groupoid case, we saw that then A and C were equal. What happens in this case here? Well, let's have a look at the P primed and then ask what is the connection between P and P primed? Well, there's actually nothing I can say, because in general it could be that they're equal, it could also be that they're not equal, one could be underneath the other or not. There is just nothing in general that I can say. So it is quite different to the inductive groupoid case. If you were to chase through these definitions, you would see that on our set of projections, all three of these partial orders are actually the same, and hence we get axiom 5 of our biordered category holding. So now if I just clean up and make use of this identity for P, so we have the domain of A sitting underneath the domain of B. Well, by this property, I know that the domain of A now also sits in the left sense underneath the domain of B. If I now look at the range of A, well, is there a relationship to the range of B? For this, again with perfect foresight, recall this particular DRC axiom. And let's have a look at the range of A. So recall A is equal to PB, let's make that substitution, and let's make use of this axiom to get this equality here. Here we're now going to substitute PB back for A, and then let's compare what we have. P is equal to QPQ, RA, RB, RA, RB. It's exactly that equality holding, so we can conclude that R sits underneath R of B. But by this property here, this is true in the left partial order as well. So in fact, we've actually just shown axiom 1 holds for the left partial order. By a dual argument, we can also show that the right partial order holds as well. And in similar ways, we can work our way through axiom 2 as well as axiom 3, the left and the right version of them. So that then gives us a biordered category. That turns this category into a projection category, and hence the P here is sorted. So now that allows me to take a DRC semigroup S and map it to its associated projection category. I can also take a different DRC semigroup, say T, and map it to its associated projection category. There is a problem though. It could be that S and T are different, yet their projection categories are the same. That's a problem if I'm trying to prove an isomorphism and I need injectivity. To get around this, I need to introduce an evaluation map, which at this point I don't want to say too much about, other than just to hand-wavily say that the evaluation of S is different to the evaluation of T in this case, and hence we recover injectivity. But I do actually want to say a little bit more about the evaluation map. So let's look at it in a little bit more detail. And for that, it's going to be good to keep track of what we are constructing and what we've seen so far. So we've seen how we can go from our set of projections to the projection category. I'm going to put a reflexive relation F, the friendly relation, on my set of projections. And this is defined as P and Q are friendly if P is the product of the domain and Q is the product of the range. From that, we can then construct paths on our projections. So a path is just going to be a tuple of projections such that every adjacent two projections are friendly with another. This allows us to define the path category. Here, our concatenation process, well, we need our end and start projection to be the same, and then we can just concatenate in the obvious way. So here we can go from our projection set using the friendly relation to get a path category. Next, I'm going to put a congruence on my path category. And this is generated by all of the relations where a path with the same two projections is just the path of the single projection. So in essence, I'm just taking out all of the repeated terms in my paths. In terms of terminology, that means I'm going from paths to now chains. So that actually leads me to the chain category, which is just my path category quotient out by all of these relations. Well, rather they're congruences, sorry. So from paths, I take a quotient by the congruence that gives me the chains. So then my evaluation map is a functor from my chain category to my projection category that needs to satisfy some properties that I'm not going to go through other than just to highlight the key one that we are going to need. And it's this one. So let's consider a chain from P to Q. So obviously P and Q need to be friendly. I can apply my evaluation map and then ask where does it map this to? Well, it maps it to a morphism, but not just any morphism, a morphism from P to Q. And that's going to be the key property we are going to use. So if we now go back to what we had, we now have our chain projection category. That is our C sorted. That's the forward direction complete. Next, we now need to go in the reverse direction, which I'm going to go through in a moment. And then we need to prove the isomorphism, which I'm not going to do today. So now we need to construct a semigroup. And for this, we need to start off on the category side with a chain projection category, and we need to end up on the semigroup side with a DRC semigroup S. And I'm going to again write this at the bottom because we have some constructing to do. What is my set going to be? It's just going to be the set of morphisms. And for our morphisms, we have the domain and range map on the category side. Well, I can use those same maps on the semigroup side. And then naively, I'm going to just hope that my semigroup product is just A composed with B. But obviously, there is a bit of a problem. What do I do if the range of A is not equal to the domain of B? What if A is all the way over here and B is over there? So that's not a great idea. We're going to need to be a little bit more clever than that. So let's set up some notation. Let's say P is equal to the range of A, and let's let Q equal the domain of B. Then I can make use of the projection category structure that I have here, which recalls sitting inside of that, we have a projection algebra. And here I can apply my unary operator, and I can define a P primed, and it actually will hold that my P primed sits underneath P in the right partial order. Dually, I can also construct a Q primed, and this is going to sit underneath Q in the left partial order. I can then make use of the axiom 3, well, the right version. This tells me that there's going to exist a unique morphism V that sits underneath A and has range precisely be my P primed. Dually, I can use the left version of axiom 3 to give me a unique morphism U that sits underneath B, whose domain is precisely that Q primed. Then by axiom 1, I know that the domain of V has to sit underneath the domain of A, and dually the range of U has to sit underneath the range of B. And then these P primed and Q primed, it actually holds that they are friendly. So that means we actually have a path from P primed to Q primed. Paths, well, I can turn that into a chain, and then I can apply the evaluation map to that. And recall, the evaluation map is a morphism precisely, in this case, from P primed to Q primed. So then I can define my semigroup product AB to be the morphism from the domain of V to the range of U. Formally speaking, AB is going to be V, composed with the evaluation map applied to the chain from P primed to Q primed, composed with U. Then I would obviously need to check associativity and that the DRC axioms hold. I'm not going to do that today, but trust me that they do, and hence we get our DRC semigroup as we had hoped. So now let's look at some of the structure comparison and recall this particular figure I had at the start of the talk, where I said as we weaken our semigroup axioms, the more structure we needed on our category side. And in particular, let's look at the 4 isomorphisms that I went through in some detail. So in the inverse case, we saw the inductive groupoid. In the DRC case, we saw the chain projection category. If I go up via the regular star case, via the chain projection groupoids, let's have a look at the category structure. We go from an ordered groupoid to an ordered groupoid. Obviously, nothing is changing there. But we go from a neat semi-lattice and no evaluation map to the strong version of a projection algebra, and we need to introduce the evaluation map. So we're adding structure there. Both of these are then found in our DRC case. Alternatively, if I go up via the Ehresmann category side, here our category structure goes from the ordered groupoids, a single partial order, to a biordered category where we have 2 partial orders. Again, an increase in structure. In terms of the object set and the evaluation map, well, they're both the same. And then that biordered category is also transferred up into the DRC semigroup case. Let's have a look at some of the applications of this work now. For this, we need to understand the functor that goes from the DRC semigroup to our projection algebra. And this is the forgetful functor, and we've already saw this, where we basically just take a semigroup, well, the DRC semigroup, and we just look at the projection set and the unary operators we can construct from the domain and range map from that. We also have our functor f, which goes in the opposite direction. So here I take a projection algebra and I map to a presentation of a DRC semigroup. So my generating set is, well, a generator for every projection. And then for every pair of generators, I have these 3 relations holding. Then our work shows that f is actually the left adjoint of p, And in fact, we can be a little bit stronger than that. P composed with F is the identity on our projection algebras. Next, we need to understand projection generated. And by this, I mean that our set of generators is precisely the set of projections. So precisely like we have the case here. Then this work allows us to generate free projection-generated DRC semigroups. If this sounds like a little bit of a mouthful, well, we can just think of this as a free semigroup where our set of generators is precisely our set of projections like we have here. And what we end up with is a DRC semigroup. If we start off with, say, just some arbitrary abstract projection algebra, I can actually construct a DRC semigroup that will have that same projection algebra. This result was already known by Peter Jones in 2021, but he made use of different proof techniques. And finally, we need to understand fundamental. And by this, I basically mean a semigroup is fundamental, that if I take a quotient of it, then two projections are going to get identified. So in some sense, the semigroup already is as fundamental, hence the name, as it can be, because any more quotienting of it is going to fundamentally destroy its structure. So we can actually do a little bit better than what we have here. Not just some DRC semigroup, we can construct a unique, up to isomorphism, fundamental projection-generated DRC semigroup with that given projection algebra. That brings us to the end of the talk, where hopefully I've given you a bit of an overview of what this project was all about. And I went through into some of the key and interesting details, but there's plenty more that I didn't cover. So for the full details, please do have a look at our full paper in the Journal of Algebra. There are some obvious future directions for this work, most notably this star regular case. And some of my collaborators are actually working on that as we speak. And they're telling me that the key step is as follows. So let's suppose I have a DRC projection algebra. I'm given one of those. And then the question is, does there exist a star regular semigroup with that projection algebra? This seems to be quite a tricky question, but also the key question in unlocking that isomorphism theorem in the star regular case. There are some more weaker semigroups, these D and DC and DR semigroups that I briefly touched on my way to defining the DRC semigroups. They all remain open. And obviously the holy grail for this project would be, or this research program rather, would be to have an ESN style theorem for an arbitrary semigroup. If I now go back to the start where I said this was going to be a tale of two cities, semigroup city and category city, well, actually, it just turns out to be a tale of one city, thanks to the strength of category theory.